basically, or essentially, what I want to do, and then I'll be finished. At the top of this table, by the way, some tables write upside down, I don't know why. You see plus 2.86. And that's the half cell potential. All the way at the bottom of this table. Minus 3.040. Okay, put hydrogen in. First, what is the reaction you're going to write? Remember, it's a table of reduction half cell potentials. By definition. Then you put the zinc. Then you put and I had that number here, 0.340. Okay. And you fill in all the other elements eventually until you have that whole table. Okay. What is this called? Is it a reduction half reaction? It's called an oxidizing agent. So things here are oxidizing agents. And your book doesn't put this in, but most books do. Strength. Strong. This is the strongest oxidizing agent. It oxidizes anything because it takes electrons away from everything. This must be the weakest because it wants to give electrons to everything. And in this column, we must have reducing agents. And this is the strongest reducing agent. Here we go, it comes down. That's not good. Okay. So you give you tables like that. When you put together a reaction, you have to take something from this column, combine it with something from this column. The best reaction if I take the strongest oxidizing agent and the weakest, the strongest reducing agent, or the weakest one down here, but I would combine an oxidizing reducing agent. This would be my strongest oxidizing reagent, would definitely react with my strongest reducing agent. On the other hand, if I combine this with this, they're both weak, they don't want to react at all. So they talk about combine something from up here with something from down here, I'm putting together things that will not react spontaneously. I combine something across this diagonal. It's a spontaneous reaction.
Can you give an example? I can't visualize it. Can you give an example?
Well, the one that I just gave here, I combined copper 2 plus with zinc. And we saw that that was a spontaneous reaction. In other words, I referred you back to when you put the zinc metal into the copper solution. That's what I started off with. The blue color of copper disappears, and you get deposits on the zinc. So if I combine this and this, I get a spontaneous reaction. On the other hand, if I were to put zinc ion with the copper metal, that was that other flask, remember at the very beginning? Nothing happened. It just sat there and looked at me. The non-spontaneous reaction. So I'm just relating it to the table of reduction potentials. Because most books do that. Your book, for some reason, doesn't, but you look at all the others, and they give you a table of reduction potentials. They put all these arrows showing you increasing oxidizing strength, increasing reducing strength. This is the weakest oxidizing agent, strongest, weakest for reducing. And if you combine a strong oxidizing agent with a strong reducing agent, you definitely get a reaction. You take something that's weak and combine it with something else that doesn't want to react, you're not going to get a reaction. So that's the connection across there. And I'll tell you about it in numbers the next time. I guess I can tell you about it in numbers now. You probably won't get to work, right? Are you not listening to me talk?
How
What?
big, how hard are the numbers?
What?
That would be awesome.
You want to see some numbers?
Yeah, let's
Okay.
see some numbers, a little taste of numbers.
This anymore?
An intro to numbers. Probably be easier to connect it later if you just see it a little bit now.
Remember good old delta G. And I said delta G maximum. I said I'll come back to this. I'm coming back to it now. And when I set up my potentiometer a few minutes ago, remember I said if I reduce the resistance, the electrons would flow one way, and if I increase the resistance, the electrons would flow the other way. And I had a reversible system. And I could do electrical work reversibly. We could talk about it for a piston, but it's pretty hard to change the pressure infinitely smallly, by infinite small amounts. But it's certainly easy to change those resistances so you only have a few electrons flowing one way or the other. So you can definitely do work coming out of an electrochemical cell reversing. I'll just put X. All I want is the units. It's so many joules per coulomb. This one says 0.2866 joules per coulomb. Right? So I can get joules out of that if I multiply by charge. W for work is proportional, like that. So far, so good. And all I have to do is put in some proportionality constants. This is joules per coulomb, so I have to say, I'll put the sign in. Oops, wrong. In other words, N is still moles of electrons. If I multiply it by volts, this is joules per coulomb, so I have moles. I need a constant. On this side, I want joules. Here I have moles. Here I have joules per coulomb. Whoops, I'm using old-fashioned abbreviation. Joules per coulomb for voltage. What must the Faraday constant be, unit-wise? It's the number of coulombs per mole of electrons. Right. And what is that? That's a mole of electrons. Right? 6.02 times 10 to the 23rd per mole. That's the way you look at this. So that's the Avogadro's constant times. And I'm not going to bother putting the sign in here because I want to put the sign in for a different reason. If I put the sign in there, I wouldn't have to say another word. But you know I like to keep talking. So I'll say another word. So I'm not going to put a sign in there. If I take 6.02 times 10 to the 23rd times 1.6 times 10, I get 96,485. Coulombs per mole. That's the so-called Faraday constant. So now we can get work, W stands for work, is equal to moles of electrons, Faraday constant, cell potential. I guess I can use the word piece. And when we put this into this equation, we have to talk about the fact that the cell does work on the surroundings. So the free energy change of the cell decreases, so we have to put a minus sign in here. I could have, like I said, I could have just left it minus 1.6, my minus sign would come out there. But I wanted to say those extra words, because the cell is doing work at the expense of free energy, and they make all these jokes, free energy isn't really free. It's just a name you give it or whatever. You have to do the work and use up free energy to get light bulbs lit or whatever. So there's the relationship. W is equal to minus NFE. So delta G and if I want standard states, I put standard states. If I don't put standard states. Now you can see, since delta G is going to be negative for spontaneous reactions, what does E cell have to be for spontaneous reactions? Positive. Do I need to write that? I'll write it in. And by the way, in some books you'll see delta capital E, and the reason your book uses U for internal energy, because those same books use UE for internal energy. Then you start seeing delta and whatever. Your book doesn't want to use the delta, so he just uses the subscript word cell. So E cell has to be positive for a spontaneous reaction, and delta G has to be negative. Okay, I'm going to combine this one with this one. And I want the spontaneous reaction. And I know E cell has to be positive. I have this number and this number. How do I combine them to get a positive number out of those two numbers? Just looking at it.
Reverse.
Well, I was thinking in terms of what you want to do mathematically. What you always want to do You always take a large number minus a small number. Mathematically, it's guaranteed to be what? A positive number. Large number, small number, I take this minus this, I get plus 2 point something. You're always taking the large minus the small. And when you put a minus here, that means you're changing the sign, right? Because this has its own sign. So you put the minus there, change the sign. If you change the sign, we reverse the half reaction, since they're reduction half reactions. If you reverse it, it's an oxidation half reaction. Now, some of the things he says there, he says almost this, except it doesn't look like he's saying this. Because what he says is, we're taking E reduction plus E oxidation. Note if I reverse this, I've made it an oxidation half reaction. And I add the two half cell potentials. That's what I've been doing as I've been going along here. But now here I'm just saying, look at any set of numbers you're given. You always take the larger minus the smaller, and we're only talking about reduction potentials, okay? We're always going to take the larger minus the smaller, it's going to be positive. So the larger that's 1 equal 3 or something. So that's the cell potential. Yes?
Just to make sure, when we're making evaluations, are we always going to see it as reduction, or are we going to sometimes see it as oxidation?
The table information I will always give you the way chemists do it, not biochemists. I'm always going to give you reduction half cell potentials. In other words, I don't follow his rule for always putting the reduction on the right-hand side, but I'm not going to mess with this table. The only way you might see it different is some of the books put this up at the top and fluorine down at the bottom. I don't know why they do that, but some books do that. And then all the hours would be reversed, of course. So what I've done is combine something along this diagonal. And that's why I said that's always the spontaneous diagonal. And the reason, when I do that, I get a positive E cell. I put the numbers there to back up what I said in words. Or I say in terms of a stronger and weaker oxidizing agent. Now I'm saying it with numbers. I'm calculating a positive E cell. That means it's spontaneous. If you have a positive E cell, then the delta G has to be a negative number. The thing that goes with it, 0.340, I didn't change. But I changed this one by putting the minus here, so I have to write that as an oxidation. I add them together, no electrons left over. There's your spontaneous reaction at standard states. And for this one, this was 0.340. I reversed this one, so now it's plus 0.763. I add these two. Notice one of the things here I subtracted a minus number, meaning I made it a plus number. I got this number. Here I reversed the equation, I changed the sign, I added these two things, I add these, I still get two different ways of doing the same problem. Guess what the biggest mistake people make?
The sign.
They do this, and then they reverse this again. and then they get some strange number like 0.3 or 423 or something like that. So you don't want to reverse it twice in the same problem. You either want to do it where you're adding a reduction and an oxidation with the appropriate signs, or you're taking reduction potentials and taking the larger minus the smaller. So if you're doing reduction, here's a reduction, here's an oxidation, you always add. Here you're doing two reduction potentials, you take the larger minus the smaller. And the nice thing about this one, it's going to tell you because you changed the sign, which is the oxidation half reaction. And now you just have to sit there and do a bunch of problems till you really get it right for the quiz.